Okay, perfect.
All right, so our next speaker is invited to talk, Guido Pagano from Rice, and he'll be talking about trapped ion quantum simulation of molecular electron transfer.
All right, thank you so much for inviting me. This has been a very interesting conference for me, since there will be many talks on two topics that I've been very interested in lately, which are quantum chemistry and open quantum systems. So I hope to put together these two topics in my talk. Since this conference was a little bit theory heavy, to catch your attention, I will modify the title. Instead of tunable dissipation, I'll say that we simulate electron transfer with programmable analog Lindbladians, which is exactly what we have. So we have basically, we manipulate the coherent interaction, the coherent evolution of a single qubit ion with Raman transitions using a ground state qubit, and we use an ancilla ion to perform controlled dissipation, to basically perform reservoir engineering. And in my talk, I will try to make a connection on why trapped ion systems can actually do interesting simulation in this field through the spin boson model. So I will explain the mapping from the spin boson model to quantum chemistry. And this is the link to the paper if you're interested. And then I'll also discuss some follow-up theory work that we've been doing, seeing how we can scale up this scheme, this programmable quantum simulator for open quantum systems, and I'll discuss the progress in building a new experimental system to do that. So let me start from the beginning. There have been some talks about ions. I will, since I have a little bit more time, I can introduce the system. So we trap this self-arranged Wigner crystals of charged particles. So you can see here a video of us loading an ion chain. And so since these atoms are charged, we cannot trap them in 3D with static fields. We use actually a time-varying electric field. We use quadruples. And so once the atom equilibrate around the equilibrium position, the competition between this 3D confinement, this 3D harmonic confinement and Coulomb interaction give rise to this very non-local normal modes. And these are really the workhorse that we use for quantum simulation, quantum computing. Basically, you can rewrite this Hamiltonian to second order as a collection of harmonic oscillators. You can trivially quantize these degrees of freedom. So this is for the motional part. For the qubit, I'd like to spend a little bit of time showing what kind of flexibility this platform offers. So at Rice, we use Ytterbium-171, which is a different ions from what was presented in the past talks, which was calcium. So Ytterbium-171 has a very nice clock qubit. So I think this is the world record for T2 time with dynamical decoupling, 10 minutes. So this qubit is very robust to magnetic field noise. It can be manipulated very effectively with Raman processes. And then it can be detected with high fidelity with spin-dependent fluorescence, similarly to the calcium ion, as you have seen in the previous talk. However, atoms have many levels. So we chose these two for the ground state qubit, but there are other qubit encodings. For example, Ytterbium has these two metastable states. They can be used as, actually, they are used as optical atomic clocks. They are not the best qubits, but for example, they can be used for cooling. And this is what I will show in this talk. Or they've been recently used to perform Raman processes on top of this quadruple transition, since this matrix element is actually quite significant compared to, for example, calcium or other ions. So on top of that, you also have a metastable qubit. So you can actually use this other state in Ytterbium, which has a lifetime of several years. So this is really use a PTB to basically implement the most accurate atomic clock on Earth. And you can transfer the ground state qubit, both the amplitude here, and you can use, for example, this for ancilla or partial measurements, and people are, this has not been realized yet, but you could, in principle, also use this for coherent operation. So if you're more interested in this type of architecture where you use different qubits to perform different operations, you can read this paper here. This is very, very interesting. All right, so for this talk, so at Rice, we basically achieved the control of the ground state qubit, and we also use this optical qubit to perform very precisely tunable sympathetic cooling. So now I discussed the external degrees of freedom, the qubits. Now we want to couple them together to actually perform some quantum simulation. So this has been covered already in previous talks. I'll give a little bit more detail. So this bichromatic drive that you apply to this ion chain basically off-resonantly excite this transverse modes, and this basically gives rise to an anti-James Cumming to a James Cumming Hamiltonian. And so if you combine this anti-James Cumming and James Cumming Hamiltonian, you can see that the natural native Hamiltonian of the system is a spin boson model. And is a multi-mode spin boson model because each spin I is coupled to a mod M with a certain coupling strength, which is given by the nature of the specific mode we are addressing. There are some detunings that we can also tune, and of course we can add single body rotations. And we can choose the phase, whether this is a sigma X or a sigma Y. So yesterday, has been shown that if you go in the dispersive regime, where these coupling are much smaller than this detuning is basically the distance between this, the bit knot and the transverse modes, you realize an effective transverse field Ising model. And this is because you can basically integrate this normal modes. And the nice thing is that basically the long-range character of these normal modes are inherited by this Jij matrix, and so you have a long-range interacting system. And so that's why even if it's 1D, it's actually quite interesting. And yesterday it was shown also that if you crank up a magnetic field along one direction, you can actually have an effective XY model, which is also long-range. So this is to highlight that there has been a lot of activity on this transverse field Ising model with long-range interaction because it breaks integrability, so it's actually quite challenging, even if it's 1D, to perform numerics. And you can see these two reviews if you're interested. The typical experiment is basically a dynamics non-equilibrium experiment. So we quench this Hamiltonian much faster than J and B, and we let it evolve the system. And then we can measure, we have single site resolution, so we can measure in any basis, for example, magnetization or spreading of correlation. And we can also go to higher order observable, like for example, in this paper, we measured the domain wall probability, which is an observable for which you will have to solve the Schrödinger equation to actually predict the value. So there's been, this is a non-exhaustive list of results on spin simulation. So there have been many, many body localization, time crystals, dynamical phase transitions. I'm sure we'll hear more about confinement in Federica's talk, hydrodynamics. So this is a very, powerful platform. However, the trapped ion platform is so flexible that it can actually talk also to different communities. So there has been a growing interest in simulating condensed phase chemical dynamics, and this will be basically the topic of this talk. And all of these are analog quantum simulation. For the lattice gauge theory in nuclear physics or high energy physics models, well, in this case, apart from the very first one, which simulates the Dirac equation, all these are basically digital simulation. So we'll focus on this paper here. And so let me introduce the problem, why we're interested in electron transfer. So electron transfer is really ubiquitous in nature, from solid state to biomolecules. And usually, you can schematize it in a cartoonish way in having a donor that has some excitation that has to basically transfer this excitation to an acceptor site. And this process can be direct or can have, catalyst or intermediate sites. So, and what makes it really hard is that basically the whole thing, for example, in biomolecule, happens in a very complicated environment. And so what quantum chemists do, they use the, as we have seen, the open quantum system technology. So they basically cut the boundary of the system at some point, and they model the environment in many ways. I mean, one of them is the Lindbladian, but there are also other more refined way. Why trapped ions can be connected to this? Well, if we take the toolbox that actually, let me show you a little bit more, some evidence of why this is interesting. So a question that I always get asked is, how can, a quantum effect matter in this type of wet biomolecule that are hot and they have a very, complicated environment? There have been already, since 1974, evidence that in some proteins, electron transfer actually deviates from the typical Arrhenius exponential behavior in temperature. So the rate actually deviates already at 200 Kelvin. And so this is quite close to room temperature. And so people, for example, have performed experiment, 2D spectroscopy experiment on this FMO excitons, and they've seen coherences in these quantum bits that last for hundreds of femtoseconds. And so there have been a lot of debate on whether this is really a quantum effect or not. For example, some people say that this is purely due to vibrational coherences, so it's not very interesting. Other people say that it's really the electron that has some coherences that doesn't dephase despite the environment. But electrons and phonons and vibrations in these systems are strongly coupled. So one might think that there is actually a vibronic coherence that plays a role. But these systems are pretty messy. So, for example, this experiment was done at 77 Kelvin. This one here was done at actually 80 end room temperature, and you can still see some beats in the signal. So these systems are messy, and that's why we want to address them with the quantum simulator and try to answer the question: what is the role of coherences, if any, in this in this type of electron transfer biomolecule processes? So why trapped ions? Well, if we put together all the toolbox that I showed you before, so we have, for example, we can implement natively, of course, an energy landscape. We can have an XY model. And then on top of that, we can also couple this spin to bosons. Well, this is exactly the type of Hamiltonian that quantum chemists use to model this type of excitonic processes. And so you have basically an energy landscape. This usually they work in the manifold with only one excitation. Then this excitation can hop on different sites. But the tricky part is that basically all these sites are coupled by this. They can be strongly coupled to a collection of vibrations. And so there's been a recent review in Nature Chemistry that shows that actually, that asks the question whether noisy analog trapped ion simulation could have an edge in simulating these models. So, for example, they use the MRG to time-dependent DMRG, and they see that there is an exponential dependence in the ratio between lambda, which is this quantity here. It's the ratio between the spin-phonon coupling and the typical vibrational energy, and the Nj. So when basically this reorganization energy, Nj, the electron hopping, are of the same order, it seems that the MRG struggles, and the exponential, the time of the simulation, the classical simulation, grows exponentially in time. So this was without dissipation. For dissipation, actually, things get a little bit trickier, but in a sense, dissipation helps you numerically because it prevents entanglement to spread out too fast. And so in this paper, I think this is kind of the state of the art in simulating these kind of models with the matrix product states. And they can simulate, for example, 20 sites, but in 60 hours, 20 sites with the 40 modes in 60 hours. So they're still pretty demanding classical simulations. So now let's move on to our experiment. So what we did, we took the simplest possible model where you have only two sites. So you have basically only two states. The excitation is on the left or on the right. And then we map it to a qubit because we have only two states, so that makes things simpler experimentally. So this spin up and spin down will be our donor and the acceptor. And then we couple this spin to a bosonic mode. And if this Hamiltonian here, you can write down the energies quite, easily. So you have these two, if you wish, Born-Oppenheimer surfaces, two harmonic wells that are displaced by the spin-dependent force, by this, spin-phonon coupling. And we can tune also omega, which is the harmonic energy. And on top of that, we can also use single body terms to basically change the energy difference between donor and acceptor, and also the coupling of these two surfaces. And so all of these parameters can be tuned with this Raman process that basically creates both single qubit rotations and qubit phonon coupling, basically. And so here you can see that, for example, we can tune both, this is simply a Rabi flopping, and this is a characteristic spin hopping, spin phonon evolution. So we can calibrate very precisely all these four parameters. But this is not the end of the story. So, of course, this is a very simple single qubit Hamiltonian coupled to a boson. But in these systems, you actually have a bath of many oscillators that are linearly coupled to this bosonic mode. And so one might think, well, you're doomed, because how can you simulate a very large collection of harmonic oscillators that have a continuous spectral density? That in this case we chose to simulate the ohmic one, which is a popular choice. And so it has been shown in these two papers that actually if the relaxation rate is small compared to omega and small compared to the temperature of the bath, actually this type of continuous spectral density can be simulated with just a Lindbladian formalism. And this is this is a stroke of luck for us, because we can actually implement this in an analog way on a quantum simulator. So as I showed you before, we have this ancilla ion, and we use this basically resolved sideband cooling to cool down the phonon mode, and we can basically tune gamma, which is our cooling rate, with laser parameters. And in principle, we can also tune the steady state. In this case, we just calibrate it. We didn't play with that turning knob yet. So just to summarize, we have a master equation where we tune the coherent part using a ground state qubit of ytterbium-171, and then we use a different isotope, and we use the optical transition to do this sympathetic cooling, and to implement basically the dissipative part of the Hamiltonian. And these two are really independent turning knobs. So, if there is no spin boson coupling, we can basically operate the qubit while cooling this ancilla ion. So now, if we basically quench just the Hamiltonian, what you will see is that if the energy, in this specific case, if the energy of the two internal states is of the same order, of is equal to the vibrational energy scale, you see that there is basically this vibration-assisted dynamics. So this is not really a simple Rabi flopping, but you're really flopping between two different vibronic states. So the Rabi frequency is proportional to the so-called electronic coupling, which is the splitting between these two surfaces here, but it's also proportional to the overlap between these two displaced harmonic oscillator states. And now we can add the turning knob of dissipation, and what you see here is that basically you can think about it this way. We basically effectively give a tunable line width to these harmonic states so that they basically collapse, they basically get pumped in a sense to a steady state, and we have irreversible transfer. And so here you can see that in the unitary case, we have some decay due to experimental imperfection, like laser intensity noise, motional dephasing. However, if we apply the cooling, this dashed line is basically the ideal evolution. So we're not far, and this means that basically we can induce dissipation much faster than the other noise terms, so we can access all the transient and the steady state before our experimental noise kicks in. So this is, a sketch of the experimental sequence. We prepare both the internal state and the motional state. We displace it so that it's in the donor well. And then we switch on at the same time both the Hamiltonian and the Lindbladian. And then we measure at the end in the right basis. So in this paper, we decided to operate in the low temperature regime, where basically our n bar is of the order of between 0.1 and 0.3. So this is basically the corresponding temperature is smaller than omega. So the temperature doesn't really affect the physics here, but it's still, larger than there should be an H bar here, but still larger than gamma, so that we fulfill the condition that I explained before. So we are in the right ballpark. And so the two regimes that we can explore now, we have, 5 parameters. So the two extreme regime is basically a non-adiabatic regime, where this electronic coupling is a very small perturbation. And so the eigenstate of the system are basically vibronic localized states on the two surfaces. Or we have that, a strongly adiabatic regime where Vx is very large compared to both gamma and lambda over 4, which is the barrier, that the donor has to overcome to go to the acceptor. And so you can see that in these two regimes, the dynamics is actually quite different. So in the non-adiabatic case, there is basically an exponential leaking of the donor excitation to the acceptor state. And in the strongly adiabatic case, you see oscillations before you actually get to the steady state. So we can basically now study what is the transfer rate. So basically what is in the case of the non-adiabatic, it's very simple. We just do an exponential fit, as you saw. It works pretty well. And the simple theory that explained that is basically this Fermi-Goldner rule. So you have the electronic coupling square, the initial temperature, basically that defines this probability, the population probability in the initial state. And then you have the Frank Condon, so basically the overlap between these two displaced harmonic oscillator states. And energy conservation is enforced by this delta function, but we can actually broaden this delta function with Lorentzian, so that we can take into account the fact that we have a bath. And so if we scan now the energy in the experiment, each one of these points is an actual evolution, and we measure the transfer rate, and we see that basically qualitatively is in agreement with the Fermi-Goldner rule, but we are already outside the perturbative regime. So Vx is a strong enough perturbation that basically, we have to use the master equation to basically to compare with the data, and the comparison is pretty good. And what we can do now is, this is basically a heat map of all the evolution. So here on the y-axis you have the number of oscillation cycles, and here you have basically the energy offset between the donor and the acceptor. And you can see that even at the level of evolution is quite close. And we can actually tune the parameters. So for example, we can reduce G, the spin phonon coupling, and we can also reduce gamma, and we have much narrower features. And in this case, we enter already the non-perturbative regime, where basically the Fermi-Goldner rule really cannot explain the data even qualitatively. And here, because we have less displacement, we see less peaks, because basically the Frank Condon overlap goes down much quicker. So this is for the non-adiabatic case. Now we can switch gear and go to the other limit, where Vx is actually quite large. And so here the dynamics is quite rich, and we cannot use exponential fit to actually compute the transfer rate. And basically what we see is that we took this data with basically the same set of parameters, and we just vary gamma. So we just vary the cooling rate effectively. And we can see that if you rescale these two data sets on top of each other with by rescaling the transfer rate with gamma, they lie on top of each other, which means that basically in this case the bottleneck is really the environment. which is very different from the Fermi-Gondel rule regime. And you see that here, up to 2, roughly, there is no distinct peak. But then if you go higher in energy, you actually recover this peak because intuitively your initial state starts to become localized in this upper surface here. And so you actually start to see again peaks. So these are basically the 2 extreme regimes, the non-adiabatic case and the adiabatic case, the strongly adiabatic case. But what we can do in this simulator, we can tune, both the coupling and the ratio between basically the electronic coupling and the cooling rate. And what we see is that there is an optimal transfer regime where basically you have just the right amount of relaxation to enhance the transfer. And so here you can see that basically this phenomenon is actually quite general. It's been observed, for this simple model, it's been predicted, this is not exactly the same model, that's why this is saturating at a certain value. It's even simpler than the one that we use here, where we see that it decays for very large Vx. But basically, this type of optimal amount of noise or dephasing is basically widely observed even in the condensed matter physics, in biomolecules, and it's been explored also in a quantum simulator in this paper from Innsbruck, for example. So it's very nice that we can recover this type of paradigmatic behavior in this model, even if it's quite simple. So of course we're not the only one doing this. There have been pioneering experiments from Berkeley and from the Sydney group and Duke. I think these are the 3 groups that are really leading. And actually, right a few days after we posted the paper on the archive, the Duke group posted a paper that is quite complementary. They use a different technique to engineer their bath. They don't use direct cooling, but they actually randomize unitary spin-dependent forces. And this gives them a lot of tunability. They can use also multiple modes. So I think these 2 works really shows that there is a lot of interest in this type of simulation, and the field is growing. And so I'm very excited. And so to reiterate what basically was said in the panel discussion about going, to other communities, spending time to learn different things and try to translate the language. I spent quite a lot of time with these gentlemen here. They are at bioscience and chemistry at Rice, Peter and Jose. And of course, I have also a physics collaborator. So there is a lot of effort, and there is a language barrier in starting these collaborations, but then it's very rewarding. We basically show that we can access this non-perturbative regime. And the main question now is what happens if you add more ions, right? The obvious question, what can we do with this platform, right? If we have more sites or more modes. Well, there are many different directions. I think there is, really a lot of opportunities. You can, for example, start playing with different cooling rates on the modes to engineer different spectral density. You can couple the different normal modes and explore the effect of an harmonicity, which is present in these molecules, and people think that might be part of a very essential ingredient to take into account. You can study temperature, which we didn't do in this paper. And if you remove dissipation, actually, if you have spin-spin interaction plus spin-boson interaction, you can study spin-Holstein model, which maps to also electron and phonons in condensed matter. So there is really a lot of opportunities. And so I want to show you basically a very obvious extension of the work that we've done. This is just theory for now. So say that you have, 2 donor sites now, and not only 1 qubit, and 2 acceptor sites, and you have cooling in between. Because you have long-range interaction, you can actually, just naturally use the native Hamiltonian and have this coupling here is much larger than this coupling here. And so you can implement natively this Hamiltonian, and here now you have 4 states, right? You have 4 possible excitations. Of course, these 2 coulants are not coupled. They don't have any unitary evolution, but they're just there to provide the cooling, the environment engineering. And so what we see basically in this very simple parameter case where we have just an offset, a common offset between these two states and a common spin-phonon coupling, is that basically to really understand what's going on, you have to diagonalize this, you have to basically switch bases and go into the triplet and singlet basis, where basically you have this, 1 and 2 are basically, it's a bell pair where basically the excitation is delocalized on the two sides. And what is very interesting here is that if you write down this Hamiltonian, you have basically, triplet and singlet that are almost diagonal, but then there is a coupling between these two, these two dimers in a sense. What we see is that being in an entangled state or in a delocalized state actually helps a lot with the transfer. So we can do the same type of dynamics we've done in the experiment, and we see that entanglement delocalization actually helps quite a lot. Not only it helps in the population transfer, but it actually transfers dissipatively the whole coherent state. So you actually transfer dissipatively the triplet state from the left to the right, and that's at least it was not. I didn't expect that. And this is true also in the non-perturbative regime, where you now crank up the electronic hopping. And this is also more robust. You can even use it, for quantum computing, this is, 99% fidelity these days is not good enough, but, it's quite remarkable that in 100 cycles, which are experimentally feasible, which is of the order of the number of vibrations that we saw in the experiment, you can actually see this dissipative transfer of entangled state. And you can now, experiment and see what happens when you have, for example, 3 sites. You can do the same thing. You can, engineer the Hamiltonian so that you actually transfer, from one edge of the chain to the other, this entangled state. So I think this is really, an interesting platform that will bring a lot of, a lot of results and a lot of developments and a lot of insights on these systems. So one point is that here, what we're doing to do this experiment, actually, we have to have the possibility to initialize basically a bell pair here. So we have to have a digital analog, a kind of hybrid platform. And that's what we're building. So we have this multi-channel AOM here, where we can control up to 32 beams in frequency, amplitude, and phase. And so we want to shine them on the ions so that we have real, programmable control on the Hamiltonian that we're using. We need a better vacuum. I will not go into that into the details, but just to say that we have high optical access here so that we can put all these beams in the system. And we're also working on a new type of trap. So this is, let's say, a little bit more experimental, just for the few ion trappers in the audience that remain. But basically, there are 2 types of traps, roughly speaking. So this is actually the trap that we use to perform the experiment I just talked about. It's a hand-aligned trap, and of course, it's never perfect. It has, it's very robust. It has very high optical access, but it's not really reproducible, and we would like to get a better performance. You can go to microfabricated chip traps, and they're what they're used in quantum computing, but they have other type of problems like low trap depth and poor shielding. And they're also, more complicated to use. They have many electrodes. So what we're doing, we're basically trying to put together the best of both worlds, and we're trying to create a plug-and-play trap that is 3-dimensional and also microfabricated with this technique. With basically, this is the same company that built the trap, the 2D trap that was shown the other day. So they have a lot of expertise in building ion traps. And So you can see here that compared to this bulky object, this is quite small and more efficient, more space efficient. So because we work with ytterbium, which is actually the heaviest atom, we did a lot of work in optimizing the thermal performance of the system. So we can now load, we can use 1.6 kilovolts roughly without having too much heating. And so we're basically now we're trapping, and the nice thing is that because it's microfabricated, the trap frequency are exactly what you would expect. So that's a nice feature, and they're also very homogeneous along the axis. And with that, let me also say finally that we are also thinking about expanding the toolbox of quantum simulation to have programmable Heisenberg Hamiltonians. And here, for example, the idea is to use different normal modes of motion, like, for example, the transverse modes to implement this flip-flop Hamiltonian, this XY. And we can use the axial mode in a programmable way to create an Ising Hamiltonian. And this is possible with this new technique that was pioneered in these two papers, where you basically use a quadruple transition to perform a Raman process. And what is interesting in our approach is that now, since we want to program the axial mode, we need to have an array of individual beams that excite the transverse direction. And so we're basically creating an optical setup where we can tune not only the amplitude of this array of TM01 mode that has a very steep gradient along the axis so that we can excite only the axial mode, but we can also control the phase. As you can see here, the phase is nearly homogeneous. So this is an interesting optics project we're working on. So with this, let me thank the group, especially Vishal and Miduna, who are really the lead on the electron transfer experiment, and Abhishek and George are working on the monolithic trap, and of course Roman and the undergrad. Thank you very much.
Thank you very much, Guido, for that very nice talk. So questions, we have time for one or two. Yeah, up there.
Yeah, I didn't listen to your talk from the very beginning. So to what extent you can control the nature of the vibrational mode in the modes in the system? For instance, for some of these applications that you mentioned, you would probably want to be in the so-called stiff limit, where the harmonic potential is much stronger than the Coulomb interaction. So can you just comment on those things?
So stiff limit, so you mean that basically there is no dispersion?
Yeah, the dispersion is heavily suppressed, so your vibrational modes would then be kind of reminiscent of the optical phonons.
So I think I'm actually, that's a very good question. I thought about that, and basically, if you look at the Hamiltonian, this Hamiltonian here, so in principle, if you have multiple tones, this is the dominant, basically, Hamiltonian. Of course, there will be some crosstalk that will have to be evaluated, but to first order, you have control over these detunings, and basically you can set them equal and have basically an effective in this rotating frame. If the crosstalk are not too strong, then you will be in this stiff limit, which is important, for example, for the spin-Olstein model.
That's precisely what I'm asking.
Yeah, exactly.
And then, of course, you have some other applications where you would want exactly opposite. You would want...
Yeah, exactly. Yes.
Very extended.
Yes.
Okay.
Yeah.
Very good. Thanks.
Other questions? All right. If not, let's thank Guido again.